Will all the international students please go to the computer lab at this time? Thank you.
We're going to get started by looking at how different numbers can be used to express the same idea. So take, for example, rows of chairs in a classroom. Let's say, and this is kind of something you need to start with, I have 36 chairs. I want to arrange them in rows, columns, and it doesn't really matter how I do that, but I do want to know how many different ways I could do that. Okay? I perhaps would do one row containing 36 chairs. Can you imagine? Probably not the most effective use of space. How about 2 rows? If I had 2 rows, how many chairs would be in each? Go ahead, Mason.
18.
Yeah. 3 rows? 3 rows. What do you think? Ellie? Uh-huh. 4 rows. 9? 6 rows? 6 rows, Ryan? 6 rows, 6 chairs. Awesome. And I could go back down the line and say 9 rows, 4 chairs, 12 rows, 3 chairs, 18 rows, 2 chairs, 36 rows with 1 chair in it. You guys kind of get the picture of what I'm describing for you? These are the different ways that I could obtain an arrangement of 36 chairs by evenly splitting them up. The book has an example of yearbook pictures that if you're in the yearbook team, you would be required to use this same kind of thinking. Maybe you have a class of 36 kids and you want to arrange them on the page. 1 row with 36 pictures in it, 2 rows. You get the idea of how that can be crossed. These pairs of numbers are factors of the number 36. The example 1 yearbook example is the number 24. I chose 36. These are factors. And back in the day, you were asked to give the factors of a number, and your teacher would say, okay, give me all the factors of, let's say, 30. I always recommend starting with itself and 1 and leaving a big fat space. If it's even, then 2 is also a factor. For the number 30, for example, it would be 2 times 15, right? 3 and 10, 4, no, 4 is not an even factor, or a whole number factor, I should say. 5 and 6. I have my list complete, I hope. You know there's no more factors in between numbers when you have found there's no more whole numbers in between. Like here, there's the number 4, which we didn't use because 4 is not a whole number factor. So you don't have to search, is there any whole numbers factors between here and here? Well, no, because the only whole number between here and here is 4. And 4 is not a factor of 30. Okay? At the bottom of page 172, they ask you for some more factors or of numbers, and you could look at those at your leisure. But 30, for example, has a bunch of factors. Would you agree with me? It is called a composite type of number. It is composite because it has several factors, more than 2. Take the number 17 on the other hand. 17's factors are 1 and 17, and that's it. There are no other factors that when multiplied will create the product 17. For this reason, the number 17 is said to be prime. It only has 2 factors. So, greater than 2 factors, composite. Equal to 2 factors, prime. Prime. There is one other option, and that's the number 1. Number 1 is neither prime nor composite. It only has 1 factor, and that is itself. Prime, no. Composite, no. 1 is just 1.
And he has to go upstairs to the office and leave for the day.
And they give you some of those on the top of page 173. You can look at the list at the top of the page up there for just a few examples of what primes might look like when their factors are listed versus what composites would look like. Remember, greater than 2 factors, it's automatically a composite. If it only has equal to 2 factors, then it is a prime. Okay? The second thing we're going to review today is the practice known as prime factorization. And some of you may remember this, some of you may not. Prime factorize, prime factorization. Now, I just want to kind of give you a little definition. Uncovering only prime factors of a number is prime factoring, prime factorization. There's a couple of different ways to do it. The book shows you how to do it via something called a factor tree. Do you guys recall the factor tree? Do you guys recall seeing that? Do any of you recall something called division by primes at all? Okay, that is the way I like because it's the fastest, most efficient way to get to your answer. So the factor tree is in the book. I'm going to show you division by primes as a method to get you prime factored. Okay? So let's pick a number. Let's pick something that's large but not monstrous. Like let's say 210. I want to know the prime factorization of the number 210. You know how when you divide the division bar, you would go up and draw a line on the top and then the quotient would be written up here? Well, we're going to do the same kind of thing, only we're going to do it down, like that. Okay? So picture a normal division box. You guys have done this, don't be scared. Picture a normal division box, only instead of writing it so that the quotient lives on top, the quotient is going to live on the bottom, and you're going to see why here in a minute. What is the first prime number? And by the way, it's not 1, we've already established it. Anybody know what the first prime number is, Chris? 2. Ask yourself, is the number in the box divisible by 2? Yes? Awesome, Ethan, thank you. It sure is. What is the quotient? Is it 105? Okay. Question 2. Is that new number still divisible by 2? If yes, keep going. If no, then you ask yourself, what is the next prime? Okay, you all said no. I heard a couple no's, and you're right. It is not divisible anymore. It is now an odd number. What is the next prime, Miss Sarah? 3. Is 105 divisible by 3? Yes. Division rules state that if the sum of the numbers is divisible by 3, then the whole number is. So now we're going to draw another box. Look at how it kind of just made another little upside down division problem. We're going to place that number, that divisor, 3 now being divided into 105, which you should get 35 out of the deal, am I right? Okay. Is it still divisible by 3? No. Okay. If it were yes, keep going. If it is no, what is the next prime in the list of primes, Grace? She says it's 5. Is this divisible by 5, class? Yes. Boom, boom, 5, and now we're down to 7. Okay? Is this still divisible by 5? No. Okay, next prime is? Aiden, is this divisible by 7, class?
Yes.
The quotient of whom is a 1. You are done with this process when quotient equals 1. Does the quotient equal 1 right now? You're done. So, what you have off to the left is the prime factorization of the number 210. To answer it, you would write this way. 210 is equal to 2 times 3 times 5 times 7. Therefore, the prime factorization is 2 times 3 times 5 times 7. In order to be correct, the factors must be primes. Some of you might say, well, wait a second. 6 times 35 is correct. And it is, but it's not primes. So that is not prime factors. Prime factors are only prime numbers. Only. By the way, is 210 a prime or a composite? Composite. Why? Because it has more than 2 factors. All right, we're going to do one more division by prime example. And the thing that I like about this better than a factor tree is in a factor tree, there's a bajillion and one ways you can go. We're going to do 180 now. Upside down division box. First prime is 2. Is it divisible by 2, my friends? The quotient of 2 and 180 is 90, right? Is it still divisible by 2, my friends? Yes. Again, draw the box, draw the quotient. Is it still divisible by 2, my friends? No. How about 3? Yes, it is. Very good. 3. 3 and 15. Still divisible by 3, my friends? Box, quotient. We're done, right? Because we got a 5. Why? What's wrong with this? Keep going. I love it. Is it still divisible by 3? No. What is it? What's the next prime? And does it work? 5. We are now done. Therefore, the prime factorization of 180 is equal to, and I know some of you might already be asking, so just bear with me a minute. That. Okay? But most of you probably recall that 2 times 2 is the same as saying 2 squared. Would you agree? And 3 times 3 is the same as saying 3 squared. Okay, so the exponential version, this bottom version here, is definitely preferred. It's less pencil, right? Less writing. Okay. Something that you may or may not have learned already, and I just have a couple more things to share with you, is the term monomial. They have a book definition. A monomial is a number that indicates an amount or product of amounts. What does that mean? Two x, oh boy, there she goes throwing letters in, is a monomial because literally this means 2 times x. 2 plus x is not. Okay, because this is the sum of 2 numbers. Product, yes. Sum, no. 12 is a monomial. It is a singular numeric unit. Not a monomial. 3b squared. What do you mean? You can square variables? Yep. This is a monomial. 3 plus b squared is not. That is the sum. Happens to be the sum of 2 monomials, by the way. Now, can these things be factored? You bet they can. Take, for example, the number 12, which is very simple, right? If I asked you to factor it using prime factorization, probably wouldn't take you long. Forgive me for being all speedy about it. Prime factorization of 12 is equal to 2 squared multiplied by 3. 2 times 2, which is 4, times 3, right? But what if I said 12z cubed? How does that separate things? Well, numerically, you do the same business with the number, okay? Ignore the z cubed briefly, and there's the 12, right? What does something cubed mean? It means that thing times itself 3 times, right? So 2 cubed is 2 times 2 times 2. Or 5 cubed is 5 times 5 times 5. So what do you think z cubed might be? Wow, lots of people getting it. Nolan, go. Nolan? Oh my gosh, I am so sorry.
It's okay.
Go ahead, sweetheart.
Z times Z times Z.
Yes. I may not know who you are, but we know how to handle z, don't we? Z times z times z. So to slam it all together, the prime factorization of 12z cubed still is 2 squared, 3, then it's z, z, z. And I know those look like 2's, I apologize. Okay? That is the prime factorization of 12z cubed. And letters, just because they're throwing letters at you, it doesn't make it any harder. I'm going to do one more example with you, and then we're going to practice a couple of things. What if I asked you to do something that is interesting? How about 52 w squared x cubed. Remember what I said about the number. Deal with the number. Deal with the number. So let's deal with the number. We're going to ignore this for right now. 52, is it divisible by 2? What is the quotient? 26? Is it still divisible by 2, my friends? Still divisible by 2? How about by 3? 5, 7, 11. What's the next prime that it's divisible by? We're now at a 1. These, simply break them up. W times W. Is that what W squared is, people? X, X, X. Is that what X cubed is? That bothered me being there. Is that what X cubed is? Therefore, the prime factorization of 52 W squared X cubed is the product of all of that. 2 times 2 times 13, and I know you all think it's a waste of time, but believe me, you have to. In order for me to know that you know what you're doing, you cannot use exponents with variables when you're showing prime factoring. Because if you're using exponents, then you have not indicated to me that you understand that W squared is W times W. It's already in exponential form right here. Show me what that means. It's already in exponential form. Show me what this means. Okay?